Halo-Tectonics is a breathing coastal threshold that dissolves the line between land and sea, orchestrating the relentless rhythm of the tide to coax new architectural life from the bones of a ruined pier. Coastal infrastructure is often built as a clear boundary between land and sea. Concrete walls and platforms are designed to slow waves, salt, and erosion, but over time, these structures are still shaped by the forces they try to control. Instead of resisting the ocean, this project asks how water, salt, algae, and existing concrete can form a more adaptive coastal system. This crisis is acutely visible across the UK coastline, battered by kinetic waves, intense salt spray, and aggressive wet-dry cycles. Birnbeck Pier stands as a stark monument to this decay. Through a distinct geological architectural transformation, natural ground became rigid infrastructure, now locked in advanced hypersaline decay.
Traditional marine preservation views salt and waves as destructive forces, but Halo-Tectonics flips this paradigm under a revolutionary premise. Salt is not the problem. It will be the solution. By redefining waves as harvestable energy, architecture transforms from a passive victim into an active producer of biological resources. The entire project orbits around a single core innovation, the prototype microalgae tile and concrete base system, serving as the central node of a completely closed-loop circular economy where biology, fabrication, and architecture become one.
We propose a closed-loop biorefinery deployed across 6 phases. Phase 1, bedrock mapping and ruined concrete excavation. Phase 2, microalgae collection and Victorian ruin grinding. Phase 3, biorefinery, prototype casting. Phase 4, macro infrastructure construction. Phase 5, microclimate curation and biopigmented tectonic finishes. Phase 6, closed-loop regeneration and continuous biomass harvesting. Ultimately, this intervention reclaims the pier as a symbiotic threshold, orchestrating the active coexistence of human transit, marine research, and multi-species rewilding.
Here, we tested the tile composition as a surface for algae collection. Different ceramic samples were inoculated by submerging and dripping, then compared by how much algae they captured, how evenly it spread, and how well it stayed on the ceramic texture, and then returned to the salinity dripping setup for continuous saltwater exposure. Under the microscope, we could see whether the algae stayed as a thin surface layer or became trapped in the pores and rough areas.
To capture this biomass, the tiles are shaped by a computational subdivision that controls both their overall form and microscopic texture. Genetic algorithms optimize the system by calibrating surface textures against simulated splash dynamics. This establishes a localized inverse relationship. Areas with slower residual water flow receive higher surface roughness directly, maximizing the physical entrapment of microalgae from ambient marine splash zones.
This diagram shows how the tile surface moves from digital design to fabrication. Where water stays, where salt collects, and how water moves are translated into ridge spacing, groove depth, and groove direction. The tiles are then placed into the site model and tested as clusters, especially through the oblique angles between assembled units. The selected models are fabricated through 3-axis clay extrusion. By changing surface roughness, depth, and direction, we can adjust how the tiles interact with water flow, wave impact, and algae attachment. Some toolpaths shed water quickly, while others hold more moisture and trap more algae. We then scaled up the test with printed ceramic tiles. In the tank, we simulated waves, splashes, dripping, tile angles, and nutrient levels to observe water movement, wet time, and the stability of algae collection. Microbial biomass naturally binds to form salt crystals in hypersaline environments. We exploit this natural phenomenon as a passive, machinery-free harvesting strategy, using the evaporating salt itself to efficiently trap and collect the microbes. This harvested biomass is refined into zero-waste bioproducts, primarily ectoine. When mixed into new concrete, ectoine forms a biomimetic hydration shell that blocks further salt infiltration, creating a closed loop where the salt threatening the architecture is used to harvest its own biological defense.
A bespoke 3D subdivision algorithm governs our structural logic, precisely minimizing concrete excavation to drive the circular economy. By utilizing finite element analysis to map wave and gravitational forces, this script mathematically optimizes our voxelized load-bearing geometry. The result is a highly bioreceptive concrete substrate. As the tide recedes, it is revealed not just as a structural anchor, but as a thriving home for marine species. These systems converge at the macro scale, where our environment-driven layout maps, annual wind exposure, and aggressive tidal shifts to dictate the foundational grid of the site. Extending this logic into a section, we differentiate carving depths and elevate building mass to generate a differentiated topography.
Altogether, the entire pier is shaped by the rhythm of the weather. The architecture is designed to work with the tides, welcoming the ferry to safely berth at high water before the sea recedes to leave behind natural pools for children to explore. Inside, the terminal acts as a warm gateway for the community. Along the outdoor walkways, the building breathes with the sea, wrapped in a textured clay skin that naturally gathers wild microalgae from the ocean spray. By learning to welcome the water instead of fighting it, Birnbeck Pier is finally reborn, becoming a living threshold shared equally by humans and the marine world.